Welcome to lesson 105. What we're going to do today is put some margins of error on our measurements. And in particular, what we're going to be measuring is a percentage. So it could be like you're taking a poll to find out what percentage of the people approve of this or that, or it could be you're taking things off the assembly line to try to figure out what percent defect rate you've got. Whatever the percentage is that you're measuring, we could put a margin of error on it, which is kind of nice. It's got these funky formula things going on, but I'll show you how they work. It's actually going to feel kind of cookbooky, really. This is actually going to be a fast lecture, I think. But anyway, here's a specific example. We'll start with a polling example. Polly the Pollster wants to measure what percentage of Iowans are feeling the burn. Now, I don't know if you remember this, but if you go back a few years, Bernie Sanders was making a serious run for president, and people who were all excited saying, "I can't wait to vote for Bernie," they would say they were feeling the burn. Anyway, go back in time, pretend that Polly is back in time, and she's trying to figure out what percentage of Iowans are feeling the burn. So, how are you going to do this? You're going to take a sample is what you're going to do. So she randomly selects some Iowans and asks them, "Hey, are you feeling the burn?" and tries to figure out what percentage of them really are feeling the burn. Now, a little bit of nomenclature here. The sample size, when she selects 80, right, that's the sample size is 80, and we use a little n to stand for the sample size. By the way, this is actually worth mentioning. Make sure you take a random sample. Don't just grab 80 people all from the same, grocery store or something, because that won't be random. Anyway, a random selection of 80 Iowans. Okay, cool. And finds that 49 are feeling the burn. Now, remember when we used to use X to stand for the number of successes? Well, we'll use X here too. So X is how many said yes, and 80 is the total sample size. And to get the point estimate for the proportion, you would basically take the 49 over 80. If you want a formula, you could write this, but it's 49 over 80. And that comes out to 0.6125. That's our best guess based on the one sample. 61.25% are feeling the burn. Now, I have to say a couple things here. First of all, this is not really P. This is what we call P hat. You need a hat. The hat signifies that this is from the sample. This is not the real value of P. This is our best guess of P. It comes from the sample. It's our point estimate is what we call it. So you put a hat on there to make sure you're kind of keeping track. Look, that was my sample. My sample said 0.6125. Okay, so don't forget that hat, please, for your sample. Another thing to think about, is that the right answer? Do you think we got it right? Do you think we nailed it on the first try? Do you think if we sample another 80, we're going to get exactly 49 again? I don't think so. So you have to keep in mind, this really is a best guess. Well, it's not a guess. I guess it's not a guess. We're not guessing. We did take a sample. But it's a best estimate. We don't know this. We don't know that. We don't know that it's 0.6125. There's gonna have to be a little bit of uncertainty here. And the good news is we can actually estimate a margin of error. So how do you do that? Well, that's actually what's up next. Let me change colors so I can keep track of myself a little bit better here. Change. Okay. So find the margin of error, find the E, and we're going to use a 95% confidence interval. So remember that lecture talking about confidence. How confident are you? When you say you're 95% confident about something, what you're kind of doing is admitting there's a 5% chance you're wrong. But you can choose different confidence levels. Look up here. You can use 99%, which means you're only 1% chance you're wrong. 90%, there's a 10% chance you're wrong. You can choose different confidence levels. Usually 95 and 99 are the two big popular ones, but we got a couple more up there just so you can play around. Anyway, we're going to use a 95% confidence level. Now, the first thing I like to do is look up the Z alpha over 2 for a 95% confidence level. Okay. Something worth mentioning, that's all one symbol. It's not like there's a Z and there's something else that's an alpha. Don't try plugging anything into this symbol. It's just a big complicated symbol. These numbers are the Z alphas over 2. So since we have a 95% confidence level, we just basically cross-reference here and say, oh, well, what you're saying is we got to use a Z alpha over 2 of 1.960. Okay, cool. So once you get that done, you can come over to this error formula, and you'll see the first thing it asks for is the Z alpha over 2, so that's cool. We can put that in there. Now it wants the p hat. Now it wants the p hat, which is 0.6125. It wants the q hat, which is 1 minus the p hat, basically, all over the n, which is the sample size, which is the 80. There we go. Plug in, make sure you can do this on your calculator, right? You should get exactly the same thing as me, and by the way, I mean exactly the same thing as me. You should get a 0.1068 for your margin of error. Ain't that something? So we're saying basically 61% with about a 10 or 11% margin of error. It's a big margin of error. That's what we got. So, okay, here's a special skill that you want to have. And this is actually important. State the results using a confidence interval. A confidence interval is, first of all, it's an interval. It's kind of like saying what's the lowest, what's the highest possible value. And then you have to talk about how confident are you. You have to say, this is 95% confident, or whatever confidence level you're using. So it involves those pieces of information. But what you're basically doing is you're saying, I think the real P is basically somewhere between p hat plus or minus the margin of error. So without the hat, we're talking about the real proportion, the true answer. The p hat, again, comes from our sample, the margin of error we just calculated. So what we're doing is we're taking our p hat and subtracting this to get our low end. Our low end is 0.506. And then we're taking our p hat and we're taking our e and adding them together to get a 0.719. And then we're writing down right next to it that we used a 95% confidence level. Do you see all the pieces here? Achtung! You shall put the confidence level. I mark it wrong if you don't mark the confidence level. Why is that being picky? No, it's because without the confidence level, that's meaningless. That's meaningless because you'll get different answers for different confidence levels. So you have to say what the confidence level is, or else you haven't said a thing. I'm hoping I can get rid of all these. Oh, really? Oh, there we go. Cool, I got rid of the squiggles. So make sure you include your confidence level with your confidence interval. Okay, please. While I'm on this little topic here, P.S. This is a good practice that I just followed. I don't know if you noticed, but I kind of knew that I wanted 3 decimal places. So while I was working the problem, I was using 4 decimal places until the end. And that's to help make sure that things round off correctly. So if you wanted 3 decimal places for an answer, you carry 4 decimal places until the very end and then round back to 3. That's a very good practice for any technical calculations. Otherwise, your answer is always different than everyone else's answer. In fact, it'd be even better to carry 5, really. But 4 is usually pretty darn good. So anyway, that's just an aside, really. So back to what we were playing with. We were playing with margin of error formulas. By the way, do you like that? Basically, you take your n and you take your sample size, you take your number of successes or whatever you want to call it, one divided by the other gives you your estimate. Then, according to your confidence level, you look up one of these things, these z alpha over 2 things, and use it in your formula for margin of error. And then it's just a matter of add or subtract the margin of error from your p hat in order to get an interval. It's called a confidence interval. That is what we've been doing. That's the whole thing. We're going to do this a couple more times. Let's see, what can we do different? Example 2, recalculate. Recalculate the margin of error in example 1. Really? Except this time, use a 99% confidence interval. Okay, well, what's different here? If everything's the same, we got the same number of Iowans and the same number of people feeling the burn and all this other stuff, it's obviously the same formulas. But if you're using a 99% confidence interval, that's going to change this thing. So come up to that table again. If you're using 99%, you're going to have a 2.576. And so that changes the calculation of the E, of course, because instead of having what we had, the 1.960 in front, we're going to have a 2.576 in front. But the inside's all the same. Our P hat is still 0.6125. We're still going 1 minus 0.6125, and we still had a sample size of 80. That's all the same. But because we changed the confidence level, which changed this, we end up with a different margin of error. We end up with 0.1403. Compare. We used to have a 0.1068. Now we have a 0.1403. So a higher confidence, 99% instead of 95%, a higher confidence gives us a larger margin of error. Now, why would sometimes people think that's counterintuitive? It's more confident, so why is it a larger margin of error? Well, when you say 95% confidence interval, what you're saying is there's a 95% chance that this interval is big enough to have the answer in it. If you want to be more sure that your interval has the answer in it, make a bigger interval. Use a bigger butterfly net. A bigger interval is more likely to contain the true value. I just think of butterfly nets. I want to make sure that the true value is in my interval. Well, make a big interval then. You want to be 100% sure? Make an infinite interval. It'll be in there. It'll be in there. Okay, so try to keep in mind a higher confidence is going to be actually a wider interval. Okay, what's this next one? Recalculate for example 1 again, but this time assume Polly interviewed 10 times as many Iowans and found 10 times as many feeling the burn. Well, if she interviewed 10 times as many Iowans, that means instead of 80, it becomes 800. And instead of finding, how many did she find? She found 49. Instead of finding 49 feeling the burn, she finds 10 times as many. Notice the P hat's going to be the same. 490 over 800 is the same as 49 over 80 is the same. That part's the same. And back to 95%, huh? So this part's going to be the same, the z alpha over 2 thing. What's going to be different? Well, if you look closely, this margin of error formula has n in it, right there. So the E is going to be, I should be actually looking up at this one, it's going to be the same as this formula, 1.960. We're going to have a square root of, the P hat was still, what the heck was it, 0.6125. And then this is still a 1 minus 0.6125. And then that's all over. It's not 80 now. It's 800 now. And so that changes the calculation of E. And this time you get a 0.0338. Now compare that with our original 0.1068. It's much smaller. Whoa, hey, you. Go back. Okay. So let's make a comment here. Not that color. That color. So a larger sample, you had a smaller margin of error, which means you can be just as confident that it's in a narrow interval. So it's like it's better, right? It's better. A larger sample shrinks your interval. That's good. That means that you're nailing it. You're getting closer to it. So I guess I'll just write larger sample size is generally better. Larger samples are generally better. The margin of error is smaller when you use a bigger sample. We like small margins of error when we can get them. Okay, 3 down, 2 to go. Let's get away from the polling stuff. So what do we got here? Wally. We got Wally. He just got 10,000 bolts in a big box or something. He wants to estimate how many of these are up to snuff. So he samples 300 at random. There's our sample size. Finds 20 bad ones. I guess we're saying a bad bolt is a success. Whatever. He finds 20 bad bolts. Now, with 95% confidence, how many bad bolts are in the whole shipment? Well, for 95% confidence, we have to look up the Z alpha over 2. That's the first thing you do. So let me kind of undo some of this stuff. We'll have to go back up to that table now. Ready? 95%, we're going to use, not that, we're going to use that. 1.960. Where are we? 1.960. Okay, cool. So now we can use the margin of error formula, which is Z alpha over 2 square root of P hat Q hat over N. That's the general formula. We got a 1.960 right there. Our P hat, oh, I forgot to calculate our P hat. Jeez. P hat equals 20 over 300, which comes out to, let's see, I already did this. What does that come out to? That comes out to like 0.0667. So just kind of squeeze that in there. So up here where the P hat goes, 0.0667. And then we'd want to go 1 minus 0.0667. And then the sample size was a 300. And when you work this out, push the buttons and stuff, you end up with a 0.0282. That's our margin of error. So now we do one of these deals. The real P has to be somewhere between our P hat plus or minus our margin of error. And so that's given us, if you take the P hat and you subtract the margin of error, you end up with a 0.0385. or 3.85%. If you take the P hat and you add the margin of error, you end up with a 0.0949. Don't forget your confidence level, 95% confidence level. That is our confidence interval estimate. Now, always make sure you're answering the actual question. What's the actual question? The actual question is, how many bad bolts? How many bolts? It's nice to have a confidence interval, but that kind of wasn't the question. How many bolts? Well, you would have to, 3.85% of them, 9.49% of them, somewhere in between. We had 10,000 bolts, so take your percentages as decimals and multiply by 10,000. So that means somewhere between 385 to 949. That seems like a lot of bad bolts to me. That's our actual answer right there. 385 to 949 bad bolts. Quincy, the QC technician. Running an assembly line, he is. So you have to sample off the assembly line to make sure everything's still good. So he randomly selects, and again, the randomly is important. Don't just take 180 in a row. It's got to be random. You don't even want to say every 5 minutes. You want to be really random. Wait 5 minutes, wait 12 minutes, wait 2 minutes, wait 17 minutes, something like that. Randomly is important. Anyway, selects 180 finished products. So that would be his sample size, I guess, 180 products. Has to reject 4. So we're calling rejection a success, but whatever. He has to reject 4. X is 4. We want a 99% confidence interval for the rate of defects. Okay, well, our estimate for the rate of defects is 4 out of 180, our point estimate. and that comes out to a 0.0222. So 2.22% of the ones we sampled were bad. They were defective. But we want to form a 99% confidence interval estimate. So for 99% confidence level, we look up the Z alpha over 2. And if you trust me, that came out to 2.576. It's in that table at the top of page 1. That's our Z. Now, let me come back up here. Now we can calculate our E. It's got the Z alpha over 2. It's got a square root of P hat Q hat over N. That's the formula. So we put the 2.576 here. The P hat is right over here, 0.0222. Q hat is the same as 1 minus P hat, 1 minus 0.0222 over the sample size, which is 180. And when you plug that into your calculator carefully, you should get 0.0424 for our margin of error. So now what? Now we do the P is got to be within P hat plus or minus E. So you take your P hat, this, and you subtract this to get your low side, and the low side is negative 0.0202. And then you take this again, but you add this to get your high side, which is 0.0646. But wait, negative? We're not going to have a negative proportion. You're not going to have less than 0, right? You're not going to have less than 0%. So rewrite this way. 0 less than P less than 0.0646. And do remember your confidence level. You must state that. And so that's our 99% confidence level estimate for the rate of defects on this assembly line. It's somewhere between 0 and like 6.5%. I suppose where it starts at 0, you could probably just write it this way, right? That would work. It's somewhere less than 0.0646, and no, it's not going to be negative. Okay, so like I say, it's kind of cookbooky today. We're just using the same kind of formulas and the same little Z alpha over 2 table over and over and over. I do want to contrast this because sometimes people mix this up a little bit. Contrast what we're doing today with what we've been doing not too long ago, like lesson 103, binomial distribution stuff. See, what we did before, maybe I'd get a brand new color. What we did before was we did things like this. Hey, P equals 0.70 for whatever it is we're looking at, flipping coins, whatever we're doing, flipping dice, anything. In a sample of 80, in other words, we're going to roll the dice 80 times or whatever it is we're doing. How many successes would we expect with 95% confidence? So remember, we would say, oh, this is binomial, well, actually, let me say this. This is Bernoulli trials. You're doing something over and over, and the chance of success is the same with every try. And so for Bernoulli trials, you use what's called the binomial distribution. And for the binomial distribution, we have these three formulas. Mu equals n times p. Remember, mu was called the expected value. You could say it's what we'll get on average. And the n is, 80, and the p is 0.70. So 56 is what we expect on average over the long haul. But then we had this formula for the sigma. Square root of npq, square root of 80 times p is 0.7 times q would be 0.3, and that comes out to something like 4.1. And then remember this, you would go mu plus or minus 2 sigma to get our low and our high values. And if you do it on this thing, 48 less than x less than 64. And we said that it was 95% confidence level, and we did say approximately. What's different about this compared to what we've been doing? Well, this, we know what proportion, what the P is, the percentage is. It's 0.7. This dice comes up as a 6, 70% of the time, or whatever the heck it is. And what we're doing is we're going to roll the dice 80 times, and we're saying, well, what range do I expect? I expect 56 on average, but how many do I expect if I keep doing this? What range will it fall into? And so this is the calculation. Mu plus or minus 2 sigma says, yeah, you'll probably get somewhere between 48 and 64. What we're doing here is the opposite. We don't know what the percentage is. We're trying to figure out what the percentage is. That's why we're taking a sample. And so we're coming up with our point estimate over here. And then we have to put an error bar on it. And so it's kind of the very opposite, right? It's the opposite. We're trying to figure out what the P is. So that's why the formula is different. And hopefully you can believe that now. Yeah. So actually, in particular, this is actually very important because I see this mistake a lot. So keep in mind, please, when you're doing it this way, hey, I know what P is. Tell me how many I should expect on my next trial. There's a 2 here. Mu plus or minus 2 sigma. Over here, do you see a 2? There's no 2. I can hardly believe how many times I've seen people put a 2 there. You don't put a 2 there. It's P hat plus or minus E, and that's it. E is the margin of error. There's no need to double the margin of error. E is the margin of error. So that's just something that I've seen a lot of people kind of mess up, and I do mean a lot of people. So it seems to be some kind of a natural mistake. Try not to make it yourself. Okay, so that was cool. That was fun. I liked it.